Okay, so we're going to do an example of applying Newton's method to solve an equation. So we're going to solve x squared equals 2. So we should be getting the square root of 2. Okay, and what we're going to do is we're going to pick an initial guess value that is going to cause us to converge on the positive square root of 2. Okay, so that we're going to find one particular solution to this. Now, I want to find that solution accurate to 3 decimal places. So I'll show you in the example of how you ensure that it's accurate to 3 decimal places, but I kind of wrote a description of how you do that up here. The idea is to estimate a solution to f of x equals 0 to some desired degree of accuracy. What you're going to do is you're just going to keep iterating the formula, iterating this formula, getting closer and closer guesses until the change in the guesses, like the n plus first number minus the nth number, is sufficiently small. So basically until it stops changing significantly. And then you'll start to see the decimal places agreeing with one another. And if they agree with one another out to, say, the 4th decimal place, then you can conclude that it's accurate to 4 decimal places. That's kind of the idea there. So first of all, to apply Newton's method, we need to be solving an equation specifically of the form f of x equals 0. This equation is x squared equals 2, which is not of that format. So the first thing we need to do is mess with this a little bit. You can take any equation and get it to equal 0 by just subtracting one side and moving it over to the other. So let's just do x squared minus 2 equals 0. Okay, that's what we want to solve. So that means the function I should use, f of x, is going to be x squared minus 2. All right, I'm going to need that. I'm also going to need f prime to do my formula. F prime of x is 2x. There we go. So that means my iteration formula is going to be xn plus 1 equals the previous number, xn, minus, and then a fraction. And the fraction has f of xn in the numerator. So f is x squared minus 2. So I'm going to do xn squared minus 2. And in the denominator, it's f prime of xn. So since f prime is 2x, it's going to be 2xn. So there's my iteration formula. What I want to do is decide what my initial guess is going to be, and then go from there, applying the formula. So x1 is going to be, for this example, I'm going to pick my initial guess as 1. I know 1 squared equals 1, not 2. But I know that my x value that I should be getting here is somewhere between 1 and 2, because 1 squared is 1 and 2 squared is 4. And so since 1 squared is slightly closer to 2 than 2 squared is, right? If you think about 1 versus 4, the 1 is closer to 2, right? So that means 1 is going to be a closer guess than 2. So I'm starting with 1 as my guess. So then x2 can be calculated by taking the 1 and plugging it into my iteration formula. So it's going to be 1 minus, and then 1 squared minus 2 over 2 times 1. So I'm just sticking in the 1 for xn, wherever xn appears. And now I can calculate that. That is, that's going to be 1 minus 2 over 2. So that's negative 1 over 2. 1 minus negative 1/2 should be 1.5, or 1 plus a half, 1.5. So my first guess is 1. My second guess, which should be more accurate, is 1.5. And yes, true, 1.5 is a little bit closer to the solution I'm looking for. But let's iterate it again. What you do for x3 is you would take 1.5 and plug it in this formula. 1.5 minus 1.5 squared minus 2 over 2 times 1.5. And if you calculate that out, you should get, that's about 1.4, oh, actually it's exactly 1.416 repeated. So here are our sequence of numbers so far. Okay. Now, doing this by hand is actually kind of silly because, you know, calculators and computers can do this so much better than we can. And so I'm going to show you a nice way to do this with a TI-84. If you have a TI-83 or some other TI, you can probably, most of them are able to do this. So I think hopefully you should be able to see my screen okay there. I'm just going to show you what I'm doing. I'll narrate what I'm doing and show you over here. So what I want to do first is use this STO button. So STO arrow, just above the on button over here. That STO button, what it does is it takes a value and it stores it, I think that's just short for store, in whatever variable you want. Now I'm going to be using the x variable, which is up here. This button is x. And so I can just grab that and use that. So what I want to do is start with 1. I'm going to take my initial guess 1, and I'm going to store it in the x variable. So I'd have this 1 arrow x that I get from that. I hit enter, and then it just tells me, okay, now x is 1. Now if I hit x, it's 1. I can do things with x, like I can say 2x plus 5, and it would evaluate that when x equals 1. This is a useful feature of your calculator that you may wish to use sometimes for other things. But what we're going to do with it now is we're going to type in the iteration formula. So we're going to type in this iteration formula with x. So it's going to be x minus, and then I'm going to put in parentheses my numerator, x squared minus 2, divided by, in parentheses, my denominator, 2x. By the way, always put parentheses around your numerator and denominator, just to be safe. Otherwise, if you, for example, here, if you were to neglect those parentheses, then you would divide by 2 and then take that result and multiply by x. This is like having the x in your numerator, which is not what you want. So make sure you do parentheses, folks. So that right there, that's going to calculate the next number, 1.5. Okay, but what I want, I'm just going to hit second enter to get that expression back again. What I want is to take that number and store it, so I hit stow and it puts the arrow there, in x. And so that expression stored in x. Now if I hit enter, it still tells me, okay, now x is 1, it still tells me 1.5, right? But now x equals 1.5. See, if I hit x and hit enter, it's 1.5. So what I'm going to do is pull back that thing, that exact same expression that I just did, hit enter again, and it gives me the next one. And actually, you don't even have to second enter to get it back again. If you just hit enter on a TI, it assumes that you want to reevaluate the exact same expression that you just evaluated, like the exact same command. So you can just hit enter, and it gives you the next number. So here, x4 is 1.41421566. That's about as much as it gives me. Okay, if I hit enter again, it just does it again, right? It just iterates the formula again and gives me the next number. So x5, 1.4142135562. One more time, x6, 1.4142135562. I mean, now, at this point, it's repeating the entire number, okay? This is the exact same answer because we've now gotten to the point where this approximation is so close. It's actually so accurate that it's accurate not just out to 3 decimal places, but 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. So that's pretty good.